share my screen. Okay. And let's get started. And by the way, please, if you have questions during the talk, just either unmute and ask them, or just type them into the chat. With remote teaching, I've gotten the habit of monitoring the chat window while I talk. So please just type your questions into the chat, and I'll take them as they come. Let's make this interactive and informal in as much as we can. So thank you again for the introduction. And yes, I'm a roboticist. I build hands, I build and I program and I use robot hands of all kinds. And you might be wondering, what is it that's so hard about robot hands? And my answer is, everything. And if you imagine even, a dexterous manipulation task that's effortless for people. You reach into your pocket, maybe you have your keys, your wallet, and your cell phone, and you kind of fumble around your pocket and you choose just one of those, and then you take it out, and the others stay in the pocket, they don't fall out, right? Such a simple task, and it's still beyond what we can do in robotics with dexterous multi-fingered hands. And usually the next question after the first question is, where are we as a field in terms of dexterous manipulation? And the answer is not terribly far along. And then the corollary question quickly thereafter is, okay, well, why? What's so hard? And usually what I like to answer to that is, to me at least, one thing that's incredibly hard about dexterous manipulation is all of these components that go into it. If you think about, again, the human hand, we have the kinematic structure, the skeleton. The human hand is very, very flexible, 20 degrees of freedom, 24 degrees of freedom, depending how you count them. Then on top of the kinematics, you have the actuation, where in the case of the human hand, we have 40 plus muscles driving the hand, most of them in the forearm, some of them in the palm as well. Amazing sensing abilities. I'll get into this in a little bit more detail. And then finally, all of that controlled by the human brain, this with its incredible ability to plan and to learn. So you need all of these playing together beautifully to achieve manipulation. And I argue not just manipulation, any complicated motor skill, locomoting in difficult terrain, all the way to playing sports. Any complicated motor skill is this beautiful interplay of hardware, sensing, learning, and control. And they are inseparable. They have to advance together. They have to know about each other, which is very, very hard, especially since for some reason, you look at these 4 parts that I have on my screen, they're traditionally studied in at least 3 different departments in an engineering school. Let's say that the Mechies worry about the kinematics and the actuation, the double E's worry about sensing, and then the CS people worry about the control and learning. And we just don't get to the point where we have beautiful manipulators capable of complex tasks like the human hand. So today in the talk, I'll try to touch on all of these and the work that we do in our lab. And we kind of try to make that a little bit of our calling card, that we try to focus on all of these components together. And I'm going to start with sensing, and particularly with tactile sensing. The peripheral nervous system in people, I think, is underappreciated. Everybody talks about distributed sensing, and when they do, they imagine things over a scale of kilometers, over a continent or a country, distributed sensor systems. The human body is an incredible distributed sensing mechanism. By my very rough, back of the envelope calculations, we have more than 100,000 tactile and proprioceptive mechanoreceptors in our body. Our fingertips, we have more than 200 individual mechanoreceptors per centimeter square in the fingertips. Multiple types, and they sense contact in multiple ways. And somehow all of those are wired individually. The signals from all of those get centralized. It goes to the spinal cord, it goes to the brain. Muscles can sense their own elongation, which is a measure of how much effort, how much contraction the muscle has. All of those sensors are wired back to the brain. We don't know how to do that in robotics. I'm so envious of this amazing distributed mechanical sensing system that we have in the human body, and we should appreciate it more maybe. So this is what we set out to do for robot hands as well. This was 5 years ago. We were thinking about tactile sensing for robot hands, and there was just nothing available that we felt fit the bill for the kind of manipulation we wanted to do, which again can seem odd because we have dozens, if not hundreds of papers on tactile sensors. The distinction though was, yes, tactile sensors is one thing, tactile fingers is a different thing. And in particular, what we felt we needed for our robot hands, which didn't exist in the state of the art at the time. Incredibly rich contact data. Again, the human body, we have hundreds of mechanoreceptors per centimeter square in the fingertip. Also, coverage of curved surfaces, right? If you look again at your own fingers, skin covers even the back of our joints. We've got this beautiful accordion structure in the skin that is the back of the fingers, the joints, everything is covered in tactile sensing. In robotics, we tended to have these planar sensor arrays that would leave the corners of the finger or the edges of the finger unsensorized. And that's not going to work. If you imagine dunking your hand into a bin full of stuff, where are you going to make contact? The edges, the corners of your finger. And if those are unsensorized, then what's the point of having tactile sensing to begin with? And we wanted tactile fingers that would be easy to integrate and use in actual robot hands. And I'll get to what exactly we mean by that in just a second. So that's where we started to build our own fingers. And this is what we ended up with after a couple of years of work. This is what our tactile fingers look like. So it starts with a 3D printed skeleton. And on top of that skeleton, we have a flexible circuit board. And thankfully, flexible circuit boards, that's a technology that's really come of age in the last 5 years to the point where you can just order them. And on that flexible circuit board, we have lots and lots of LEDs and photodiodes. So for example, in this image, this is a photodiode up here. And then this is a pair of LEDs. And you can see that we have lots and lots of these LEDs and photodiodes on our flexible circuit board. On top of that, we have a layer of transparent urethane. This is just PDMS, just a simple transparent urethane. It's 7 millimeters thick. It's a little hard to tell in this photo. And this acts as a waveguide. So it's transparent, and then it just does a good job of letting light through. And then finally, on top of that, we have an opaque, thin layer. We refer to it as our skin. It's again PDMS, but it's much, much thinner, about 1-2 millimeters. And it's infused with silver dust particles to make it opaque. So how does this finger work? So I'm showing you here a cross section, a horizontal cross section through our finger. And you can see this is the transparent PDMS layer, the waveguide right here. Then on top, we have the skin, the opaque skin that's on top. And then the LEDs and the photodiodes sitting on the flexible circuit board at the base of the transparent layer. So then what we do is we measure how much light goes from every LED to every photodiode. If you think about, the LEDs in blue, the photodiodes in red, by turning the LEDs on one by one and then measuring the signal in each photodiode, we have a measure for how light travels inside the transparent PDMS, inside the waveguide, between each LED and each photodiode. And that's the secret sauce, if you wish, of our sensor. Because now, if you think about all of these rays of light that I'm showing here, bouncing around, going between LEDs and photodiodes, you can imagine that as soon as this finger makes contact with anything, the waveguide is going to deform, and all of these rays are going to start bouncing around in a different way. And those are all signal changes that we can detect in the photodiodes. Okay, so again, we look at how light travels between each LED and each photodiode, which is great because if we have 30 of each, 30 LEDs, 30 photodiodes, it means we get about 1,000 individual signals. Okay, again, looking at light between every LED and every photodiode. And this finger doesn't really have sharp edges or corners that aren't sensorized. The hemispherical tip of the finger, so this bit right here, is fully sensorized all around the circumference. Excuse me. And then the body, the cylindrical body, is sensorized around more than half of its circumference. So we don't have blind spots. We have all of these optical signals that change when the finger touches anything, and no blind spots that we care about. And this is basically what happens. This here I'm showing, here's a finger where it's making contact with something. These are our 1,024 signals, or however many we have, and look at how they change in response to touch. They kind of go haywire. Of course, not all 1,000 signals change for touch in one specific location, but many of them do. So on the one hand, incredibly rich sensor data. This finger makes contact with anything, we're going to see it. We're going to get lots of signals, and they're going to change. Beautiful signal to noise ratio. On the other hand, though, we are supposed to somehow make sense of all of these signals. This looks like they've just gone haywire. We need to make use of this and extract information from these raw signals pertaining to touch. And this is where we knew from the get-go that we're building a tactile finger meant to be used in conjunction with machine learning. That we would never try and have an analytical model of how all of these optical signals react to touch. It's possible to build it. I mean, we can do ray tracing and things of that nature. We just thought too complicated. We're going to use this very rich data set in a purely data-driven fashion. So it's a sensor for machine learning designed from the beginning with the understanding that we don't need an analytical model for these signals. We're just going to use them as input for learning. The significance of using silver dust, that's a great question. Actually, anytime when I said opaque for the skin, I should have said reflective, right? Because the outer skin, the one that's coated in silver dust, it's meant to keep outside light out, but also inside light should bounce around so that we don't lose it. So we use silver dust because we want this to be somewhat reflective. And because of that, light from this LED, for example, will bounce around a couple of times in the waveguide and then is picked up by the photodiode all the way across on the other side. So that's why we're doing silver dust, so that it's a little bit reflective. It also raises eyebrows when you purchase makeup. Silver dust is for makeup, essentially. And we have gotten questions, wait a second, why is Matei's lab buying makeup and brushes? And we had to convince people that no, it's legitimate robotics research. And another question, I say anytime the finger makes contact with anything, we sense it. And the question is, well, you need to have a little bit of pressure too. Absolutely. That's another excellent question. We sense deformation as a proxy for touch, and the touch has to be strong enough to deflect the waveguide, to deform the waveguide so that we can see it in our optical signals. But the beauty of it is optics, you get such beautiful signal to noise. So even very slight touches are enough to create to deform the skin enough that light transport changes and you get very nice signal in the photodiodes. Before building these fingers, we were building piezoresistive, and we were looking at piezoresistive fingers, and the signal to noise just wasn't there. The first time we did optics instead of electricity and we saw the signal to noise we were getting, we were hooked, never going back to electricity. Light is where it's at for us for the tactile fingers. And we're going to quantify how much pressure we need also in just a second. So thanks for the question. Okay, so let's get back to learning how this finger is used. So this is how we collect training data for one particular way of using these fingers. So here we're poking our tactile finger in highly controlled fashion. We have a UR5, a robot arm with a linear probe. At the end of the linear probe, we have a load cell. And we are poking the finger in controlled fashion so we can label our raw tactile data with things like touch location and touch force. Okay. And once we're able to collect that labeled training data, we can use it for a very standard supervised model that goes from raw signals to contact location and contact force. And this is what it looks like after it's been trained. This is the kind of, here we're detecting touch location and touch force and taking advantage of the large sensorized area, no blind spots, no hard edges or corners that wouldn't be sensorized. So this is what it looks like in practice. And then this is the actual quantification of it. Going back to the question about how much pressure we need, here we can quantify it and we can see that performance does get better as the contact force increases. So your intuition was right that the more pressure we have, the more deformation. So then the better we are at identifying the things that we care about. So once contact force exceeds about a Newton, we can localize contact with sub-millimeter accuracy. And then we can also detect normal force with usually below 10% error. So this is the kind of performance we get. But this is just the finger, just one finger in isolation. We never wanted to build one finger. We really wanted to build hands. So as soon as we had the finger, we went and we built a couple of different hands with these tactile fingers. And here you see, oddly enough, one of the things that we like the most about these fingers is the cabling or the lack thereof. This is the only cable that we need to talk to our finger. It's a 12-wire FFC. And that's because, you know, we get 1,000 signals, but with only 30 LEDs and 30 photodiodes. And we multiplex everything through time, so we address them one by one, which means we don't need 1,000 wires coming out. Robotics almost always comes down to, can you wire it up? Wiring is the death of the roboticist. And this is why we build these fingers the way we did, knowing that we wanted them to be easy to integrate in robot hands. And these are two different flavor hands we're building. The one that you see on the left, it's only 3 fingers, but it has tactile sensing both on the distal joint, on the distal links, and it can have tactile sensing on the proximal links of the fingers. And that's because all the motors are in the palm. All the motors are down here. And also all the motors are sitting on torque cells. So this hand has motor torque sensing too. The one that you see on the right is a different flavor where we only have tactile sensing on the distal links, but it's much easier to build. So it's 5 fingers, 15 degrees of freedom, no torque sensing though. And we're pushing both of these. Another very good question in the chat, what about multi-touch? What happens if you're touching multiple things? The easy answer to that is, well, if we can train for that, so for example, if we build a setup that looks sort of like this one, but train for multiple touches, which makes it a lot more complicated, then this supervised learning approach works for multiple touches. And again, we're collecting labeled training data here, and from there is just vanilla supervised learning. So if we're doing that, then we can do supervised learning for multiple touches. And we've done that, we've quantified it. So the paper where we have these results also talks about multi-touch. It's very cumbersome though to train for multi-touch. So it's a little bit of a tricky point. We'd love to go to unsupervised learning for these fingers. And that can mean both unsupervised learning in the sense of finding a latent space for the raw tactile data, or maybe doing model-free reinforcement learning that takes as input the raw tactile data. And then we don't need training data for multiple touches. We don't need training data at all. So that's what we're hoping to do in the future for the multi-touch case. For now, we're focusing a lot more on the single touch, thinking that, you know, convex fingers, locally convex objects, we're just going to get a single touch on every fingertip. But that's an excellent point about where we need this to go in the future. So what are we doing with the hands? How are we actually using this tactile data? This is the very, very current work. This is something that we submitted just about a month and a half ago, where we've shown so far in simulation that it is possible to do extremely dexterous in-hand manipulation using only what we call intrinsic sensing. So intrinsic sensing means sensors that are inside the hand. In the last maybe 2 years or 3 years, other groups have shown pretty remarkable dexterous manipulation skills using model-free reinforcement learning, but they've needed very extensive sensing setups. Let me play this video again. So they've, you know, like a network of 10 cameras, or, you know, motion tracking for the object, and that's not realistic for deployment. Here we're showing that you can do these very complex manipulation tasks with just tactile and proprioceptive sensing. The method, again, is reinforcement learning. So far, we've been able to train these in simulation where, like, you know, I'm sure many of you are familiar with kind of the revolution of model-free reinforcement learning we've seen in the last couple of years. Incredible policies for incredible skills, very, very simple and efficient. And that's also the case for us. It takes maybe, you know, 15 million simulated time steps to train a policy that's able to do this kind of finger gating, which is why training has to happen in simulation. But then it's possible you get these finger gating skills where the hand is able to pick up a finger, put it back down somewhere else. And once you're able to finger gate, then you can be dexterous and rotate the object forever, essentially. And in the paper, we show, you know, what were the various things we needed to do to make these policies learn. It's, from an algorithm perspective, it's vanilla policy gradient reinforcement learning for those of you who are familiar with RL, but we did have to play a lot with the things like the initial state distribution so that it can learn such complicated policies. And we are working right now to transfer these to the real hand. You see that the model that we have here is a model of this exact hand, the one that you see on the right. And we are confident about getting this to transfer on real hardware. So we hope that we are months away, because we're only using tactile and proprioceptive sensing, which we feel we have a good handle on, and everything is internal to the hand. But this is the kind of dexterity that we'd love to be able to show in the real world, in the wild, you know, and on a wide range of objects. And here we're taking advantage of having these multi-curved, fully sensorized fingers with no blind spots, right? Because, you know, you do this kind of finger gating, you're going to touch the object in all kinds of places on the finger. You cannot afford blind spots or hard edges or corners. And thankfully, we don't have them because of the way the finger is constructed. Okay, So the point here is that we have a sensor that's built from the ground up, knowing that it's going to be used for learning, and designed to make the high level, the policy level learning easier by avoiding blind spots and giving us coverage like we're going to need to do. Let me take a look. We have a question in the chat. Would it be feasible to tile the surface with independent patches rather than one continuous sensor sheet? Ah, wonderful question. So excellent point, right? If we do multiple patches, then we can sort of isolate touch. And it'll be easier. However, what we lose, and let me rewind a little bit, we lose this ability to, get a signal all the way from one side, an LED on one side, all the way to a photodiode on the other side, right? Because in our design, we have 30 LEDs talking to all 30 photodiodes. Because we don't subdivide the sensor, we have a very, very rich signal set because every LED talks to every diode. If we were to subdivide it, you make an excellent point that we would get localization, but we would lose some of the richness of the signal. Is that a good trade-off? We haven't quantified that. We could. We have the data. We could say, hey, what if each LED only talks to the photodiodes in its immediate vicinity? Is that a net plus or a minus? We haven't quantified that. My gut feeling is that we're better off with more data and letting learning take it from there. But it's a good perspective. It's something that we haven't quantified yet. Okay, so far we've been kind of on the right-hand side of this image, what goes into manipulation. And we've talked about the interplay between sensing, developing the sensor for the policy learning, and how they interface with each other. What about kinematics and actuation? Let's focus a little bit on the other side of this plot. And I'm going to completely switch gears on you and talk about an altogether different application. This is an application from space. This is NASA's Astrobee robot. This little guy here, it's a cube about 30 centimeters, a little more, 35 centimeters in each dimension. And there are now 3 of these Astrobees floating around the International Space Station. They were upmasked, I think, about 2 years ago. They're floating around the space station. The Astrobee was designed to be a monitoring platform. It can float around by itself. It has a beautiful impeller-based propulsion system. So it can float around the inside of the space station. It's very energy efficient. Of course, it's got cameras. It can localize itself, and it can monitor instruments for astronauts. Astronaut time is incredibly expensive, as you can imagine. And there are just so many mundane tasks and chores, essentially, that astronauts have to do. And anytime NASA has a chance to automate some of those, they jump on it. So the Astrobee, initially, they thought, how about we have a mobile platform that can monitor instruments? But of course, once you have a robot on the space station, you immediately want to have it manipulate things as well. The first kind of manipulation that NASA wanted to do, they wanted to have the Astrobee perch onto handrails. The space station has handrails everywhere because astronauts need to grab onto them, of course. So they said, look, we want the Astrobee to perch onto handrails so that it doesn't use power when it's stationary. So about 5 years ago, our lab designed a little perching gripper that NASA, our collaborators at NASA Ames, they took our design, which we open sourced, and they flight certified it. NASA won't send to orbit something that can, off gas or catch fire spontaneously. So they flight certified the design, and then they sent it to orbit. So the Astrobee has a little arm, just a 2 degree of freedom arm, and then the perching gripper that we designed, grabbing onto handrails. Just 2 months ago, they demonstrated autonomous perching, and we designed our gripper to be very robust to positioning errors. So we're very, very happy about that. But again, we kind of got greedy. Okay, well, now it has a gripper on it. Well, why shouldn't it have a hand and be able to do more than just perch? Well, what could it do? And we're lucky that one of our faculty members at Columbia is Mike Massimino, former NASA astronaut, one of the people who fixed the Hubble telescope. He knows a lot about space. So we brainstormed, use cases. What kind of things would it be useful if the Astrobee could manipulate and pick and place or deliver to astronauts? And we came up with a series of objects, shapes that we'd like the Astrobee to be able to grasp. And then it quickly became clear that if we want to do stable grasping of this range of shapes, we want more than a gripper. We want a hand. And just with our intuition, we came up with a 3-finger design. And why 3 fingers? You want 3 fingers so that you can do stable tripod grasps. If you imagine something like the tuna can, a tripod grasp would kind of come at it in 3 places, a lot more stable than a pinch. Excuse me, for a lot of round objects, we want to do fingertip grasps, power grasps as well. Okay, so we know that, for example, this design, 3 fingers, 8 joints would be very, very good for that. But we're not going to be able to put 8 motors inside of this hand and still have it fit inside the Astrobee. The payload bay of the Astrobee, where the hand needs to stow, is about 10 by 10 by 10 centimeters. You build a hand with 8 motors, it's not going to fit in 10 by 10 by 10 centimeters. It's going to use too much power. It's going to be too computationally expensive to control. You need very, very significant under actuation, which means many fewer motors than joints. We want this hand to have 8 joints so that it has the versatility to grasp all of these objects. Well, it can have at most 2 motors. 1 would be even better. So 8 joints, 1 motor, heavily under actuated. So what does that mean? Again, think about the kinematics of the hand. Let's say this hand has 8 joints, 8 degrees of freedom, and we want it to execute all of these different grasps. If you now think about what we call the posture space for this hand, okay? It has 8 joints, 8 degrees of freedom, so the posture space is 8-dimensional. Every hand posture corresponds to 1 point in this 8-dimensional space. And this is my best attempt to put an 8-dimensional space onto a 2-dimensional slide. Please imagine with me that this is indeed an 8-dimensional space that we're talking about. Okay, each of these grasps, we know how we want to shape the fingers for each of these grasps. So each grasp corresponds to 1 point in this 8-dimensional space. So far, so good. Well, what happens when you introduce under actuation? You say, okay, this hand has 8 joints, but a single motor. Or maybe 2 motors. Because it has many fewer motors than degrees of freedom, it means that on its own power, this hand cannot access the entirety of its 8-dimensional posture space. At best, because it has few motors, so here's an example. A single actuator here, it's pulling on 3 tendons. The tendons are shown in red, and the tendons drive the joints. That's how you drive 8 joints with a single motor. But because you have few motors, on its own power, the hand can only access a subspace of its posture space. Some manifold. There's only some low-dimensional manifold that the hand can access on its own power in that 8-dimensional posture space because it's under actuated. And I think by now you can kind of tell where I'm going with this. What we want to do is shape this manifold introduced by under actuation so that it hits all the grasps that we care about. How do we shape the manifold? Via design parameters. This is where, you know, our mechanical engineering side comes into play. We put our mechie hats and say, this hand has a number of design parameters. What is an example of that? For example, if our underactuated transmission consists of tendons, many tendons connected to a single motor. And again, the tendons are shown here in red, 3 tendons connecting to a single motor and driving all of these joints. The pulley radii for the tendons around the joints, that's a design parameter. That's a set of design parameters. The springs that extend the joints, right? Tendons can pull, they cannot push. We need springs to extend the joints. The stiffnesses of the springs, the preload of the springs, those are design parameters. You change those design parameters, those mechanical design parameters, the shape of this manifold also changes. So can we optimize our design parameters such that the manifold hits all of the grasps that we care about? And it turns out that, you know, there are a couple of ways to do this. So this transmission, which converts motor force into joint torques, that's what determines the manifold shape. And the first approach that we took was very much a traditional design optimization method, where a combination of brute force and analytical modeling and optimization. I'm not going to go into the details of how we did it because I want to save a little bit of time for the next thing that I'll show. But again, it's, if you've done design optimization, it's it won't massively surprise you, but this is what it looks like when it's done. So here is our very first prototype shown here. So this was before it even had an actual motor, you know, so nothing up the sleeve, just a single slider, a person pulling on this slider, and then this slider is connected via our optimized transmission to all 8 joints. And notice how the fingers form this nice tripod fingertip grasp, then they come together and you get a nice pinch, and then they move out of each other's way and you can envelop something. And this synergistic behavior is all in the transmission, because all the person is doing is pulling on that one slider. And part of our the algorithm, the novelty of our method was that we optimized not just so that the hand can shape its finger to reach those grasps, also all of those grasps are quasi-statically stable. Manipulation is first and foremost about forces, not about positions. So we came up with new optimization algorithms to also get static, quasi-static stability. There's a question on, so changing modes to drive the motors on a different set of tendons. Yes, there's some beautiful work out of TU Delft, for example, on these changing transmission modes, where the motor can, in a discrete way, go from driving one tendon to driving another tendon, or if you introduce a second actuator that just connects or disconnects a motor from a tendon. And like you're saying, they increase mechanical complexity, but they give you more powerful things that you can do with few motors. And that's something we didn't take into account. You can do, for example, nonlinear cams, so pulleys with non-constant radius. You know, there are various games to play there, and yes, people have come up with ways to change modes in a discrete fashion. But here we're doing it without that. It's just continuous. And here you see the same prototype, but now actually with a motor. You see the same synergistic behavior. One thing that I want to point out here is at runtime, there's no sensing, there's no computation. It's all in the mechanics of the transmission. The hand choosing the grasp for the object and having stability for that grasp, it's all through the mechanical optimization of the transmission. We wouldn't have space for sensors. We wouldn't have power or computational abilities for the sensors in such a constrained environment. It's all what we like to call the mechanical intelligence in the transmission. And here is an integration test with the ground unit, the NASA ground unit at Ames, where we integrated the avionics. This is a slightly bigger prototype of our hand. The version we have now is smaller and actually does fit inside the payload bay. So we're still hoping that we might be able to do flight certification with this hand and then send it into orbit. It's difficult, you know, everything that requires astronaut time is insanely difficult, and the AstroBee project has been going on for a while with great results. We're not sure we'll be able to piggyback on the AstroBee project and flight certify our hand and send it to orbit. We're still holding out hope, and it would be terrific. We're still quite happy with the performance that we're seeing even here. So what does this mean for us? Yes, we can optimize the hardware, or at least the transmission part of the hardware. What we didn't like about the way we went about it is that all of these grasps that we want the hand to execute, they were chosen via human input. So the grasp planning part, how you grasp each object, that's the planning part. That was done by a person. Then the mechanical optimization was done by our algorithms, ensuring both position and force stability. These mechanically realizable manifolds, this is what we refer to, how we refer to our method. But we had this disconnect between the planning part and the optimization of the hardware, which was bugging us. So for that, we went to, you know, what is the state-of-the-art method right now for optimizing planning? It's reinforcement learning, and in particular, model-free reinforcement learning. And it's hard to overstate just to what level the RL revolution has just kind of swept over the robotics field. So for the last bit of my talk, let me see what am I doing on time. About 10-15 minutes left. Okay, that sounds about right. So let me tell you about how we integrated mechanical optimization into reinforcement learning. And I'm going to start with just a basic primer on RL. I'm sure many of you are very familiar with this, so please bear with me if these are things that are very well known to you. So how does reinforcement learning work? Well, you have what you're optimizing is this idea of a policy, a computational policy. The policy takes as input observations from the world given to you by your sensors. So your sensors will sense some part of the state of the world and give that to your policy as observations. And then your policy has to spit out actions, usually in the form of motor commands. Then those motor commands get sent to the robot executes them, the world evolves and goes over to the next state, and then this whole cycle recommences. So, and usually the computational policy these days, when you're doing deep reinforcement learning, the computational policy is represented as a computational graph, a deep neural network. Usually in robotics, if you're doing motor learning, it's going to be an MLP. If you're doing vision, it might have convolutional layers. In any case, it's a computational graph. The behavior of the computational graph is governed by its parameters, you know, the weights and the biases of the neural network. I'm sure many of you know how this works, right? So the weights and the biases of the neural network are the parameters of your policy. And the whole game in policy optimization in reinforcement learning, you're optimizing your policy parameters, shown here in blue, such that the actions that your policy takes are appropriate, optimal, given the state of the world. So that's the name of the game. If you're doing a policy gradient method, which many people are these days, then you need to be able to take a gradient of the actions with respect to the policy parameters, which is fine, because if your policy is represented as a neural network, as you well know, that's differentiable. You can do auto-diff through a neural network, so you can take the gradient of the action with respect to the policy parameters. Okay, so far so good. Vanilla policy gradient model-free reinforcement learning. Well, one thing that turns out happens in robotics is that these methods, they need a huge number of training steps to converge. usually in the tens of millions for the kinds of things that we see, you're not going to be able to train that with a real physical robot. You're going to destroy the robot and you just don't have the time to do it. So what people have been doing in my field is instead of training on the robot, you train on a physics simulator, which includes you're simulating all the hardware of your robot. And it's just a general purpose physics simulator treated as a black box. And there's been amazing work, not from my lab, from other folks in the field, showing that you can train on an imperfect simulator and then still apply the policy to real hardware. And the way you do it is via domain randomization. To me, that was a major step forward for the field, but it enabled us to train inside a physics engine because we need to train for tens of millions of time steps. So what we did was to say, well, wait a second. This basically means that all of the hardware of our robot is part of this black box simulator. That makes no sense. We have control over that hardware. We are building it. We are designing it. We should be optimizing some parts of the hardware along with our computational policy. Is it possible to take part of the robot hardware, simulate it not as a black box, but also as a computational graph, and optimize that along with the computational policy? And when you're simulating hardware as a computational graph, you cannot have it just have arbitrary structure, because the structure of your computational graph is dictated by the laws of physics. You are simulating physical hardware that in our universe behaves in a certain way. But for example, it turns out that something like our transmission mechanism, the tendon-driven transmission mechanism, we can simulate that as a computational graph. And guess what? All of these design parameters, pulley radii, spring stiffnesses, spring preloads, those become parameters of the computational graph that simulates our hardware. It's perfectly analogous to the computational graph of the computational policy. Hardware in many ways behaves like a policy. Our transmission accepts as input motor commands and converts them to joint torque. That's what a transmission does. Any transmission converts a motor command, a motor force, into a joint torque. So it takes the motor command as input. It has parameters that govern its behavior, spits out joint torques as output. It's beautifully analogous to the computational policy. We can simulate it in a differentiable way, which means that, look, we can optimize these together. We can optimize the computational policy and the hardware jointly with and for each other, with a joint gradient that's propagating through both. Okay. So this is what it looks like. You have unoptimized hardware, unoptimized computational policy. This is what it looks like once you've optimized the computational policy that just tells you how to position the hand and when to close the fingers, and you've optimized it jointly with the model of the physical transmission. The underlying RL algorithm is just off-the-shelf gradient, policy gradient. In our case, it's trust region policy optimization. You can use others. And because we have this joint gradient through both mechanical and computational elements, we are a lot more efficient than gradient-free optimization methods. Evolutionary strategies, yes, people have been using that for a while, but because we have this joint gradient propagation and we're using these very powerful policy gradient methods, we are a lot more effective than those. And we can then take here it is, right? The pulley radius from the optimization, the spring stiffnesses and preloads from the optimization. We physically build that transmission, the mechanical policy, we build it in real life. The computational policy is running behind the scenes and determining when to close the fingers, right? This is the big advantage compared to the previous part. Now, the positioning of the hand and the closing of the motors is governed by the computational policy. It's fully autonomous. the mechanical policy has been built into and baked into the physical transmission. So I think as a field, we are on the cusp of big things in terms of hardware and software co-optimization. I mean, we've known, this is not a new idea, that hardware and software should be optimized with and for each other. This is how evolution works, right? Evolution doesn't put complexity in hardware that the software has no use for. You know, our bodies and our brains evolved together with and for each other to take advantage of each other. But what is new is that we have much better physics simulators. We have these amazing ways to transfer optimization done in simulation to reality. We have cloud computing to run these, tens of millions of time steps. And we have these very powerful deep reinforcement learning methods that can optimize computational policies. So you put all of these together, and I think we're about to enter a new golden age for hardware and software co-optimization, and I'm excited about what the future holds. And the bigger point to me is, if you look at all of these components, where does intelligence live? And of course, artificial intelligence is the hype these days. It's inescapable. We're a golden age of artificial intelligence. Overhyped, maybe, probably. I think many of you might agree. Okay, good, fine. We live in the age of artificial intelligence. Where does intelligence reside? And the knee-jerk reaction is in the brain. Of course, intelligence lives in the brain. And we're saying no, intelligence doesn't live just in the brain unless you're doing chess or Go or abstract games. If you are doing physical tasks in the physical world, then you need embodied intelligence. And once your agent has a physical embodiment, then intelligence isn't confined to the brain. Intelligence can live in the kinematics and in the actuation. And these optimized transmissions that we have, we like to think of them as examples of mechanical intelligence. It can live in the sensors. If you design your sensor knowing about the policy that's going to use that data, that frees up completely different design spaces than if you're designing your sensor in a vacuum and you don't know how it's going to be used. So, conclusion number one, driving our research agenda, at least for us, intelligence can live everywhere and can have physical embodiments. Conclusion number two, we're going to do the greatest things when we optimize these together with and for each other. And that's, we're very excited about what the future holds. So with that, I want to give a big shout out to our research group, our collaborators, and thank you very much for listening today. I appreciate your attention today. Thank you.
Thank you. This was awesome. Let's see if we have other questions.
We do have 2 questions in the chat. Do I have time to, should I go through them?
Quickly, yes.
Okay, so the first question is about the touch sensor. Depends on light. So how are the designed fingers going to work in spaces where there might be less light or brightness? Oh, I cannot even begin to tell you how much work we put in making sure that outside light stays out, right? That's the reason for the skin, the outer skin. So this skin right here makes sure that outside light stays out, so it doesn't interfere with our measurements, that we only, inside the finger, we only get light from our own LEDs and photodiodes. It's surprisingly hard to build something that is flexible, soft, and opaque. And the way we do it is by infusing PDMS with these silver particles, and then also we do carbon particles and more layers than we had to. The driving thing was about 2 years ago, we had to do a high-profile demo of these fingers in direct sunlight. And it's because our eyes do such a great job of adapting, we don't realize how much brighter the sun is compared to our indoor light sources. We took our fingers in the sun and nothing worked, and we were panicking. We had this demo in a week, nothing was working outdoors. We were vampire fingers. You put them in the sunlight, everything goes crazy. And then finally, with enough layers of these coated PDMS infused, dust infused PDMS, we were able to keep outside light out. So now we are fairly robust to ambient light. We don't really care much about how much ambient light is out there. But great question, brings back memories that I thought I had blocked out. The second question, will the pressure be different for particular tasks with no gravity? Wonderful question. So the hand that we have right now is designed to, this transmission will behave the same way with gravity or without gravity, because we made the springs so stiff and the motor so strong that gravity becomes a lot less significant. But that means it's over-engineered, right? The motor is stronger than it needs to be because the springs are stronger than they need to be. But until that happened, I didn't appreciate what a hard time NASA has, right? Think about it. If you're NASA, you're building something for microgravity, you have two choices. Either you build something that only works in microgravity, but then you cannot test it until you send it up, or you build something that also works in surface gravity, but then it's by definition over-engineered. So, you know, I wouldn't want to have that problem. They are amazing people that, you know, the fact that they're able to do that. So yes, our hand is over-engineered so that it works in surface gravity the same as in 0G. Are the sensor data pre-processed to train the MLP, or is the raw sensor data, the raw used? Great question. So what we do is, well, yes, we do pre-process it in this supervised training fashion. So first we collect training data the way you see here, and then we train our supervised model that takes as input the raw tactile data and spits out just 3 variables. Touch location, which is 2 variables because the skin of the finger is a 2D manifold, and normal force. So the first thing that happens, the raw tactile data, 1,000 signals, goes through that model and it spits out touch location, touch force, 3 variables. And then only those 3 variables go to the policy that does manipulation. Okay, this is how we've done it so far. What we'd like to do in the future is to be able to pre-process the raw tactile data without having to collect labels. So to do it in unsupervised fashion. And of course, there is a wealth of research on unsupervised learning, on learning latent spaces. It's been harder than we thought. We've struggled with this for, I'd say, more than a year now. We haven't given up. Maybe we can also use just completely model-free RL end-to-end, where the raw tactile data is fed as an observation to the policy. That's tricky because it's 1,000 signals. We don't know yet, but we'd love to use the raw data. And then one more question, which metrics do we use to evaluate the efficiency of the RL hardware software co-design problem? Well, great question. So the first one always is the reward. And I don't have the reward function shown on this slide, but of course, policy optimization aims to optimize the reward function. How much reward engineering goes into your work? Nobody wants to tell you in RL papers, and we don't tell you how we spend months tuning our reward function. The reward function for training, we give a reward eventually when the hand is able to grasp the object to a specific height and hold it there for a specific time. So that's the reward that's explicitly optimized. And then once we physically built the hand and we're running it on a real robot, then we have more of a metric, which is, grasp success. You put the object there, we hit go on the computational policy, and does it succeed in lifting the object stably and holding it there? how many times out of how many times, 5 out of 5, 4 out of 5, and things like that. So for now, our metric is just success in lifting the object. For more complicated tasks, like this finger gating, the metric that we train with, for example, is object revolutions. How many times are you able to spin the object around its own axis in a given amount of time? So that's the metric that we use for dexterity without dropping it. Metrics for dexterity, it's a fraught and complicated topic that there's little agreement on in the community. There is even little agreement on whether there should be agreement. Do we need standardized metrics? Many people will say, of course, how do you do science without metrics? Other people, kind of myself included, say manipulation is so complex, it doesn't lend itself to metrics for everybody. We should each have our own metrics, but there isn't one metric for everybody. It's a complicated and, endlessly discussed topic in the community.
Thank you so much for the wonderful talk, Dr. Ciocarlie. I have to have a good discussion with you about embodied intelligence versus disembodied cognition. I think that is a whole discussion by itself. I would probably talk to you offline about that. But
absolutely.
Thank you for the great presentation.
Thank you so much. Thank you for the invitation, and thank you everybody for joining.
Bye.
Bye. Thank you.